Okay, we're back. This is AP Physics 1 check-in number 5. This one has to do with the work, power, and energy. So we're going to ask you some questions. Probably saw the document. If you haven't seen it, take a look at the questions and then try to pause and then answer as per usual. We've got a picture here of an object sliding across the surface. It's being pulled across the surface with a force of 250 newtons at an angle of 35 degrees. The mass of the object is 22.45 kilograms, which is the same as 250 newtons. As well, when it slides across, it goes through a distance of 6.75 meters. And the question being asked is, what is the work done on the object by this 250 newton force? So we're quickly going to go on to the equation and say that work is force times distance times the cosine of the angle, because you really only want if you look at this picture, you only want the x component of that force. So you want the component in the direction of the displacement. In this case, that would be the x component. So you could put in your numbers, and I'll give you an answer and see if you can go back and do it. 250 newtons is the force. The displacement is the 6.75 meters, and then put in the cosine of the angle. Make sure you're in degree mode, 35 degrees, and if you do that, you get an answer of 1382. The units would be newton meters, which are joules. So that's the amount of work that force does on that object. It says, now if there's a coefficient of friction, because it was actually a rough surface, and that coefficient is 0.25, what is the work done by the frictional force as the object moves 6.75 meters? So go ahead and try that. The frictional force will act in the opposite direction as the force, so it probably would look somewhere on the surface like that. So in this case, you're probably going to have to figure out what is the amount of friction, and that will be equal to the coefficient times the normal force. If you look at the free body diagram, I guess the weight force, if you look back up at that object, the weight force is down and the normal force is up. Now the normal force is not necessarily equal to the weight, because there is part of this force that's pulling up at an angle. So you would have to find out some things about that. So you'd have to figure out what the so maybe we'll put a question mark there. What is the normal force that acts on that? So let's go ahead and do some calculations here. The y component of that force would just be F times the sine of the angle. So it would be 250 newtons sine of 35 degrees. If you do that again, you get 126.2 newtons. If we draw our picture of that object, we have a weight force we said was mass times 9.8. If you took the 22.45 times 9.8, you get 250 newtons downward. We now know that there is a force of a y component equal to 126.2 newtons, and the difference between that would give you the normal force. So I would go ahead and subtract from 250 126.2, and that I believe is the normal force. If you do that, it's just under 100. It's 93.8 newtons. That's your normal force. So the frictional force is equal to the coefficient times the normal force. So I'm going to put 0.25, which is a dimensionless quantity, the coefficient, times 93.8, and that will tell you how much friction. And that turns out to be 23.45 newtons. Now the work done by friction is just that frictional force times the displacement. And again, that's going to go through a 6.75 meter distance. So if you take that 23.45 times 6.75, that'll give you the work done by the frictional force. If you do that, you get 158 joules. Okay? So I think that's the answer to the question, was how much work was done by the frictional force, and I think we've calculated that to be 158 joules. Our goal is to quickly move on. And I believe there's a third part to this that says, if the object starts from rest, what is the velocity after it gets to the end of that 6.75 meters? The purpose of that question is for you to realize that work is force times distance, but it's also equal to the change in kinetic energy. That is what we call the work energy theorem. Does that make sense? The work energy theorem. Sorry about the bad writing there. But work is change in kinetic energy. So the net work in this problem would be the work done by the force forward minus the work done by the frictional force. And the two numbers for that were 1,382 joules minus 158 joules. So the total amount of work is 1,224 joules. So that's the amount of kinetic energy that's gained in this process, which would be the final kinetic energy minus the initial kinetic energy. But if it starts from rest, that's zero. So the final kinetic energy, if you're following me, should equal that. So that should just be 1/2 mv final squared. Does that make sense? So v final would just be 2 times that, if you use your algebra, divided by the mass. And the mass was the 22.45 kilograms. And then I'm going to have to take the square root. And if you do that, you could double check for me, but I'm getting like 10.4 meters per second, somewhere around there. Okay, so that was a pretty long problem, but that gives you an idea of how to do a work energy and work calculation problem. The next one is pretty straightforward, and we're going to do it quickly so make sure we get through this video. How are work and energy and power related? Okay, so power, if you remember from class, is the rate at which work is done. Rates are anything divided by time. The other way to look at it is, how does it relate to energy? It's the rate at which you change your energy. So that could either be changing potential, changing kinetic, mechanical, electrical, whatever type of energy is the rate at which it goes. How much energy per time gives you how much power. Units, work, we said, was force times distance. So we already figured that out. That would be like newtons times meters, which are in fact joules. And the unit of power, work or energy divided by time, those units would then be joules per second. And a joule per second is known as a watt. Okay, that's just reviewing. I'm pretty sure you probably had the answers to those questions. Next, let's move right along and see if we can get through this last problem pretty quickly. You have a skateboarder going at the top of a first hill. He's actually moving, goes down, and goes up to the top of the second hill. And we want to know, by the time you get to the bottom of the second hill, how fast were you going? So what is the final velocity of that problem? So the idea on that is maybe that we take a look at some energy conservation. So let's do an E equals E prime kind of thing. The potential energy plus the kinetic energy at the beginning should equal the potential energy plus the kinetic energy at the end. I hope that makes sense. I think at the end, if you move that to the other side, that's going to be the change in potential energy plus the kinetic energy will give you the kinetic energy at the end. And so we're going to use that together. This will be mg change in height. This will be 1/2 mv initial squared is then going to give you 1/2 mv final squared. Notice that all those terms have an m, so they effectively can cancel out. If you're multiplying each term by the same number, it can then cancel out mathematically and not affect your answer. So if we put in some numbers, we should be able to get an answer to this. 9.8 meters per second squared times the height. Change in height would be 18 meters minus the 10 meters at the top of the second hill, plus 1/2. It does have an initial velocity, so you have to add that in. 6.5 meters per second quantity squared is going to equal 1/2 the final squared. You should have the math tools to be able to solve for that. But if you do that, I got that the final velocity, and you can email me if this isn't right, but I think you get 14.1 meters per second. Go ahead and check that, see if I'm right with that number. And we're going to do one more part to that, and that is, how about if it loses energy as it goes down? It says that the mass now is 50 kilograms and it loses 2,000 joules of energy as it falls. What is the speed at the top of the hill, the second hill? So we're still going to use energy conservation. It's just, I might add a piece to the puzzle, which would be how much energy is lost over there, because E prime will be in fact less than E. So we're going to keep going with this and say, well, it's the potential plus the kinetic equals the potential plus the kinetic plus the 2,000. If you want to add in 2,000, then you're going to need to make sure that you put in the mass this time. The mass can't cancel. So you put in your MGHs and your 1/2 MV squareds. But you just need to make sure that when you put in your 2,000 joules at the end, you haven't canceled the mass, because that wouldn't be mathematically correct, because the 2,000 does not include the mass of 50. So you have to multiply those in. 50 kilograms times 9.8 times the height of 18, so on and so forth. And I think that will leave you with enough, and I may allow you to do all that algebra and see what happens. But if you do that, I get that the final velocity is now reduced to 10.9 meters per second, whereas it was 14.1 in the last problem. Here it has reduced to 10.9. At this point, I think I'm going to say that's it. I'm going to let you go ahead and put in those numbers. Again, let me know if that doesn't work out for you, but I hope this is useful. We'll see you next time. Thanks a lot. Stay safe.